Good morning, ladies and gentlemen. It is Wednesday, February 3rd, and today we are going to be wrapping up the week by talking about Newton's laws of motion. So far this week, we've kind of gone over velocity, acceleration, and then yesterday we took a look at the acceleration motion graphs and how that looks on both the distance versus time, as well as the velocity versus time graphs. So if you haven't done that yet, make sure you finish up that lesson. It's going to be a big part of the quiz, which is tomorrow. Hey, announcement, tomorrow is your first test. It is over the first 2 weeks of material. It must be done in person with a coach. So make sure that you can make it into the building on tomorrow. If you cannot, make sure you reach out to your coach and set up a time to get that done. If there's some reason you can't make it in the building, you need to reach out to me so we can figure out another way to make sure you can take the quiz under supervision. On the quiz, while I'm thinking about it, guys, you can always, like I say, always use a calculator. And then also in the Google Classroom, at the very bottom under the general resources, there is the formula card. So make sure you're also using that as well. There'll be more formulas on there than we've gotten to because it includes all of them, but you should recognize the ones that we've already gone over for distance, or for the metric system: distance, displacement, speed, velocity, acceleration, and one more that we're going to be going over today with Newton's laws. So without further ado, we're going to go ahead and get started on the Newton's laws and free body diagram notes. So please make sure you have those guided notes open. I'm going to share my screen now. Here we go, share the screen. Okay. So we can now talk about an object's motion, about whether or not it's in motion. We can talk about how far it goes. We can talk about its displacement. We can talk about how fast it goes. We can talk about if it speeds up or slows down, all of that wonderful stuff. And a lot of what we've been able to do in analyzing motion and stuff like that really comes back to our understanding of how motion works. And the person that spent the most time talking about how motion actually works in the natural world was Sir Isaac Newton. So today we're going to be talking about Sir Isaac Newton's 3 laws of motion. All right. First off, we have to define what is a force, okay? A force is either a push or a pull on an object. And a force is either going to cause the object to start moving, stop moving, or change direction. Hey, that should sound familiar. Speeding up, slowing down, or changing direction. What does that sound like? That sounds a lot like acceleration. So a force is going to cause an object to accelerate, speed up, slow down, or change direction. Okay. All objects are constantly experiencing forces. So this is going to be one of those hard things where we have to think about normal everyday occurrences in a very abstract way. The key here, though, is that this, if we put an apple on the table, the forces that we are not seeing are still acting. So the reason the apple doesn't begin to magically float into the air is because of the force of gravity. And the reason that the apple doesn't fall through the floor is because of the force of the table pushing up. So we're going to be talking about forces. You may have thought about gravity, but you didn't think about that upwards force. So this is what we're going to be talking about today, thinking about all the forces that act upon an object. Okay, this brings us to Newton's first law. Newton's first law, we have to go all the way back to the Greeks because we really need to understand what was the scientific understanding for motion up until Sir Isaac Newton's time. And the Greeks were the first kind of group of people to really talk about this, or one of the first. And Greeks thought that the natural state of objects were at rest. And this just came from very simple observations. If a ball was rolling, eventually it stops rolling. If something is moving, everything that they saw would eventually stop moving. So that's what made them believe that everything's natural state was at rest. That in order to not be at rest, you had to expend energy and things like that. However, what the Greeks did not know about was the force of friction, okay? Without friction, objects would not stop moving. They would continue to move forever. That rolling ball would just continue to roll forever. So they didn't have the full picture, which is kind of what led them to think the natural state of things was at rest. Newton, however, and the story goes, he's sitting, he's pondering this kind of stuff, seeing an orchard or whatever, and depending on your interpretation of the story, either an apple falls in front of him or he gets hit on the head by the apple. But this kind of leads him to think about what caused that apple to move, why was it moving, why was it not moving, things like that. So it kind of leads him to his first law of motion, which he borrows from the Greeks. Newton's first law of motion says an object in motion tends to stay in motion. And an object at rest tends to stay at rest. And the other key part about that is unless it's acted upon by an unbalanced force. Now, what's an unbalanced force? We'll get to that later. Okay, but what you need to understand is basically an object that's moving is going to stay moving. An object at rest is going to stay at rest. If you have an apple sitting on a table, it's at rest. It's not moving. It's going to stay on that table until another force acts upon it, like you pushing it or someone knocking it over or picking it up. So the key here is that the object in motion is also going to stay in motion. I'll give you an example of that makes that a little bit more clear. So if you're moving and you keep moving, you're going to stay in motion, okay, until you run into something or you stop, which causes you to stop. So where can we see Newton's first law of motion in practice? Well, this is sometimes called the property of inertia. Inertia is a property of matter that causes it to resist changes in motion. Okay. Now, what affects how much inertia an object has? Well, an object with a greater mass has a higher inertia. It's going to take more force to move that object. Think about if you've ever tried to move a piece of furniture. The smaller the furniture is, the easier it is to push around. But if you've got a huge bookshelf or something like that that has a high mass, it gets a lot harder to move that around the room. Okay, and that's because of this property of inertia. It takes more energy to start that motion. And this normally is a little thing, but hooray for Google Slides not having all the animations. So I'm going to pull it up just real quick in PowerPoint so we can see this little animation because I think it's important. Okay. What are we doing things today? Oh, way too far. Okay, so here's a little animation that I wanted to show you guys, okay? So inertia and Newton's first law is the reason that you need to wear a seatbelt in a car. So for example, we have this little motorcycle rider, and the motorcycle rider apparently doesn't see this giant brick wall in front of him, but he's moving along at a nice constant speed. All right, object in motion stays at motion until the bike stops. And why does the bike stop? Well, the bike stops because it runs into the wall. So there's actually a force from the wall pushing back onto the bike. Now, what happens to the person? Well, unfortunately, there is no force to stop his motion. There's no seatbelt or anything like that. So what happens when he runs into the wall is he's in motion. So he continues to be in motion until he's acted upon by the force of the ground. Okay, so that's why it's important to wear your seatbelt. Because even though the car stops, or in this case, the motorcycle stops when you get in an accident, it doesn't mean that you're going to stop. Anything loose in the car that was in motion is going to stay in motion. All right, this brings us to Newton's second law. All right, Newton's second law is kind of a very simple formula. Force, the force of acting upon an object equals its mass times its acceleration. So what do I mean by that? Let's say you had a car ran out of gas, you got to push it to the gas station. Say your car weighs 100 kilograms and you're able to cause that to accelerate at 0.05 meters per second squared. So I can use this formula to figure out what force you are exerting on the car. It's very simple multiplication. The mass is this 1,000, the acceleration is 0.05, and all you really have to do is multiply those numbers together. Now, what are my units? You might ask. Well, the units are very simple. Don't worry, the mass needs to be in kilograms. The acceleration has to be in meters per second squared. But when you do that, you're actually just going to combine them into something called a Newton, which is this big N right here. So we measure force in newtons. That's a nod to Sir Isaac Newton, the person that gave us this idea of forces and things like that. So newtons are the unit for force. So if you take 1,000 times 0.05 in your calculator, you're going to find out that you will wind up with an answer of 50. And 50 what? 50 newtons. Now, how does this formula work? What factors would change how much force this car has? Well, there's two things. Either the mass can change or the acceleration can change. If I push this twice as hard, that's going to increase that to 0.1, and that's going to make this 100, right? So it's very important to understand that the more acceleration, the more the force. The same is true of the mass. If I keep the acceleration the same, which means I can still push the car at 0.5, like in the second example, still pushing the car at 0.5 meters per second squared, but now I'm pushing a van, which has twice the mass. If I can cause these two cars to accelerate at the same rate, the reason for that is I have a bigger force acting upon this van, because 2,000 times 0.5 gives me 100 newtons of force. All right, and then again, it's a direct correlation. I doubled the mass. What happened to the force? The force doubled when you kept acceleration the same. So important to understand. Force equals mass times acceleration. That's simple. Drop the units at the end, slap on an N for Newton. Now, the forces on a person standing are balanced. Gravity is pulling you down. So right now, if you're sitting in a chair, gravity is pulling you down into that chair. And the reason you're not falling is that chair is actually pushing up on you. This upward force is one that we don't often think about. Okay, we often think about gravity. Anyone who's stepped on ice or tripped, you've had a very rough lesson in gravity. Pulls you down, but we don't often think about the upward force keeping you in place. Again, force equals mass times acceleration. So the key here is that this is not going to change. When these forces are in opposite directions and they're of equal, value, they're going to cancel each other out, and there's going to be no overall motion, no acceleration. So an object will only accelerate if there's an unbalanced force. Now, if I came in here and I push this guy to the left, let's say, if I push him from behind, he's going to start to move in that direction. The reason for that is there's nothing balancing out his force over here. Okay, so it's really important. All right, so if I came over here and I pushed this guy, he would start to accelerate in that direction. The reason for that, nothing is here. Now, if there was a wall here and I would push against him, I would push this direction with my force. The wall would push the opposite direction with its force. He would still be balanced. He would still not accelerate. So an object is only going to accelerate if and when an unbalanced force acts upon it. So Newton's first law, object in motion stays in motion, object at rest stays at rest, unless they're acted upon by an unbalanced force. Newton's second law is, how do I figure out force? Force equals mass times acceleration. And this brings us to Newton's third law. Newton's third law tends to be a little bit trickier because it's not often one that we deal with very much, and it's a little bit harder to think about. But what is Newton's third law? Newton's third law states, for every action, there's an equal and opposite reaction. Okay? So what they're showing you here is if you're in outer space, right? And let's say you're trying to fix something on the outside of your spaceship, and something happens and you fall off the spaceship and you're floating away in the deep outer space. You have to get back to the spaceship or you're going to die. Well, you can use Newton's third law to help you out, because if you have something in your hand, you can use that to actually propel yourself in the opposite direction. So this astronaut was floating away, and what happened was he threw this rock. Okay, so he pushed the rock to the left with his force. But for every action, there's an equal and opposite reaction. So as he is pushing on the rock with his force, the rock is actually pushing on him as well in the opposite direction. This is hard to think about, but if I push off on this rock, the rock is actually also pushing on my body. So if I throw this rock in the opposite direction from my spacecraft, it will push me back very slowly to my spacecraft. Okay. This is also, so like I said, astronaut pushes on the rock. rock pushes on the astronaut. Now let's bring this back to Earth, because there are also examples here on Earth where we can see Newton's third law. And this is for anything that flies. Okay, so like birds, for example. Birds exemplify Newton's third law each and every day. So if we look at this, how does a bird fly? Well, it flaps its wings. Okay, which direction are the wings pushing? Well, the wings are pushing down. What makes the bird fly? Well, as the wings push down, what is it pushing down on? It's pushing down on the air. And guys, air, I know we can't see it, but it's a fluid and it does have mass. Okay, so if it has mass, it has force, okay, or it can be pushed upon. So what happens is the bird pushes down on the air. The air also pushes on the bird in the opposite direction, up. So the bird flaps its wings down, pushes down on the air pushes up on the bird, and that's what creates the lift, so the bird can actually take off and fly. If it wasn't for Newton's third law, birds would just fall out of the air because they wouldn't be able to fly. But because there are equal and opposite reactions, all right, the bird pushes down on the air, and the air pushes up on the bird. So this is a great example of Newton's third law. You can also experience Newton's third law if you hit a wall. All right, you get mad, you decide you're going to go punch a wall. Well, guess what? You hit the wall with a lot of force. Well, why do you break your knuckles? Or why do you break your hand? Well, because guess what? The wall hits back with equal and opposite force. Okay, so if I hit a wall, I'm putting my force into the wall is pushing back in the opposite direction with equal force. So that's why your hand hurts. Now, it's important to note that equal and opposite do not always result in equal acceleration, especially when the masses are different. So let's take a look at two little examples here. All right, here we have two objects, the green one and the blue one. And what's happening is the green one rolls in, the blue one, I should say, is at rest. So that object is going to stay at rest. The green one is in motion, so it stays in motion. And what happens is this green ball comes in and knocks out the blue ball. Now, once they make contact, there is an exchange of force here. The green ball is pushing the blue ball with its force, right? Well, what does the blue ball do? The blue ball actually pushes back on the green ball with equal and opposite force. Now, these two are the same size, so we're assuming that they are the same mass. So what actually happens here is when the green one runs into the blue ball, it transfers all of its energy, all of that force. And the blue ball, because it's the same mass, does the same thing in the opposite direction. This causes the blue ball to accelerate because there's nothing stopping it from moving. If you look over here, there's no wall, there's no other force acting upon it, so it starts in motion. And the blue ball pushes back on the green ball. Because they're equal, this causes this one to stop. Equal and opposite reactions. Now, what happens as I change the mass? Well, let's take a look at the second example. Now, the blue ball is much smaller, right, about half the size, so it has half the mass. The green ball is the same size, moving with the same force. Now, notice the differences between these two pictures. When they were equal masses, the forces were equal and the acceleration was equal. This stopped its motion, this started the motion. And they're about at equal speed. If you notice that, it's also about at equal speed. Now, if you look down here, though, the masses are not the same, okay? So what happens is as this green ball runs into the blue ball takes off, okay? And the green ball continues its motion forward. But if you notice, it actually slows it down just a little bit. The green ball, because the blue ball is still pushing back, the green ball still loses some of its speed, some of its acceleration because of this exertion of force. The blue ball, however, moves much faster because it has a much smaller mass. That same force is happening between these two pictures. Because it has less mass, it's going to accelerate a little bit faster. We can also see this as something called a Newton's cradle. You may not have heard the name before, but you've definitely seen one before. It's those little things with the little metal balls that just hit back and forth. And what's really happening here, people keep on their desks and stuff, as this ball goes out and comes back, it hits this one with the force, right? So there's many force exchanges in this example. This hits it with the force to the right. This one hits this one to the force to the left. This one transfers its energy to the ball to the right. This one hits it back with the force to the left. And then this one hits this ball to the right. There's nothing there, so it flies out. And then it comes back and exerts the same force on that one, which is why it's only the two outer ones that are moving. Because all of these balls have the same mass, they're transferring the force equally. So one stops, one goes in motion. All right, so we can see Newton's laws of motion by looking at a firing cannon, okay? I forgot to mention about Newton's third law. I'll mention it here, but this is also, there's also some funny stuff about Newton's third law that you can see it. So Newton's first law, remember, is the property of inertia, opposite that tend to do what they're doing. So opposite motion stays in motion, opposite rest stays at rest. So how can we see a cannon and cannonball operating Newton's first law? Well, the cannonball that's in the cannon is going to stay at rest until the force is put on it. What force are we talking about? We're talking about the lighting and ignition of the gunpowder. So that cannonball is not going to move until that cannon is actually lit and fires. Now, when the ball is rolling, the ball is going to continue rolling until it runs into the ramp, which causes it to change its direction, changing force. So object at rest stays at rest. While it's in here, it stays at rest. Once it's fired, it begins in motion. It's going to stay in motion until it's acted upon by the ramp of the pool. Newton's second law, the greater the force put on the ball, the more acceleration it has. So in this example, if we were to double the gunpowder, AKA double the force, that cannonball is going to move a lot faster. And conversely, if we half how much gunpowder we put in it, it's not going to be as big of a force. Sorry. So it's not going to accelerate as fast, okay? Force equals mass times acceleration. Also, the greater the mass of the ball puts a greater force in the water. This is also why I win cannonball contests, okay? I have a big mass, so when I hit the water, I'm exerting a bigger force, right? And we can see that splash, which is actually more of Newton's third law, but greater the mass, greater the force. Newton's third law, every action has an equal and opposite reaction, okay? Recoil. Recoil is an example of Newton's third law that some of you may be familiar with. There are a lot of funny videos of people on YouTube that don't know how to shoot a rifle, with a scope, that is, because what they do is they put the scope right up to their eye and they forget to put the butt of the gun in their shoulder. Because what happens when you pull that trigger? Well, the gunpowder ignites, it pushes the bullet one direction, and guess what? The gun goes the opposite direction. That's the kick, that's the recoil. So what you see is if people use a rifle incorrectly, they end up with a black eye, because what happens is that gun kicks back, there's nothing stopping that force, that motion, and so it hits them in the face. So in this example, the gun fires the cannonball to the right, the cannonball pushes the gun back to the left. So you see that little recoil right there, that little cha-ching right back here, boom, that little recoil, equal and opposite. We can also see Newton's third law with the water. The ball force is downward, that pushes the water upward. That's what creates the splash. Okay, now is a good time if you want to take a break. You can also do this later, but there is a YouTube, or not the YouTube video, but there's a Brain Pop video that I want you guys to be watching on Newton's laws. You can do it now if you want. The link is in the document, or on the classroom page. It's just that little Brain Pop thing. The username is there and the password is there as well. All right, continuing on. What does gravity have to do with it? Well, gravity is a force, right? So when you're staying on the floor, your forces are balanced. Gravity is pulling you down so you don't float away. The floor is pushing you up so you don't fall through the floor. And there is no motion, okay? Now, what happens if there's no floor there? Well, this lady is dropping a ball, and what we can see here is gravity is pulling the ball down, but there's nothing really pushing up on it. There is something pushing up on it, which we're going to talk about later, but right now, we don't see anything acting upon the ball. So what do we see? We see it start to accelerate. Now, how do I know it accelerates? Well, in 1 second, in the first second, it only moved this tiny distance. The second second, it moved more distance. The third second, more distance. The third second, even greater distance change. The fifth second, look at how big that one is. So this ball is actually accelerating downward, okay? So in this case, the forces are unbalanced. There's nothing acting upon the ball pushing it up, which is why the ball starts to accelerate in the downward direction. Now, what is acting upon that ball to actually slow its fall? Well, there is something called air resistance, okay? Here's what we need to understand. Air resistance is the opposition of the downward motion of falling objects. When you fall through the air, you're pushing down on the air is actually pushing up on you. So what we have here is we have two examples. We have this example on the left, and what this one is this is one where air resistance does not exist. This is like a vacuum. If you sucked all the air out of the room and you dropped a feather and an elephant, they would fall at exactly the same rate because there is no air resistance slowing them down. So they just fall due to the force of gravity. Now, the one on the right is a little bit different. This is what we would normally see. The elephant has a very, very, very high mass compared to its surface area. The feather has a very low mass compared to its surface area. So the air resistance acts upon the feather a whole lot more, slowing its fall because it's pushing upward on the feather, the air, okay? The elephant's mass is so strong and so big that the air resistance is not a big enough force to really affect it, or at least for us to notice it. But because the feather has such a small mass, we notice that effect much greater and it takes longer to fall. Sorry, I'm just gonna go back to the other one real quick because I've edited these notes to cut out some stuff. Okay, write down this. Okay, here we go. We read that already. Okay, this brings us to free body diagrams. So free body diagrams are a diagram that we're going to use to measure all the forces acting upon an object. So this is where we're going to start to look at what forces are acting upon that object and what is it causing it to do. So it's a sketch, and what you do is you just make a square. All right, this one's a trapezoid, but you just make a square, and in the middle you can put the mass if you know it. If you don't know it, it's fine. You just make a square. And then you need to add in all of the forces acting upon the object. Now, force, you just put F, but then you need to kind of abbreviate what kind of force it is. So in this case, we have the downward force, which we're often going to have on this planet, always going to have on this planet really, which is the force of gravity. So the force of gravity is pulling this object down. Now, why is it not falling through the floor? Well, because whatever it's sitting on is pushing up on it. We call this the normal force. Things don't normally fall through the floor. So normally things get pushed upward on by whatever they're resting on. That's the normal force. Now in this case, if I'm interpreting this because I know what it looks like, but this object is being pushed. And it's being pushed to the right. And how do I know that? Because this is an applied force. Applied means something is physically acting upon the object. Someone is pushing that or something is pushing that. So we see a big force to the right, and that is the force of applied force. Now, remember, what did the Greeks not know about that causes things to stop motion, that opposes motion? That is friction. Okay, so anytime an object is being pushed or moving, you're going to see some kind of friction. If it's on the ground, you can just put friction. If it's falling through the air, you can put the air resistance. So friction is a force that opposes motion. What we don't know is that all surfaces are actually really rough. When you zoom in enough on them, for example, this is a razor's edge. If you zoom in and you look, you can see all those little grooves in there. I don't know if you can see my mouse or not. Here's the pointer, here we go. You can see all of these tiny little grooves in here. This is not straight, but this is a razor that you would use to shave, your face, your legs or whatever. But then when you zoom in, you see all these little grooves. And what happens is those are like little teeth that get caught on things. That is friction. Every surface has these little grooves. Without friction, we would have a very hard time moving around. we would basically be like walking on pure ice. There would just be no way for us to push off or go anywhere without friction. So friction is actually a really important force for us. Allows us to move. But friction is also the reason that things stop moving, because all these little grooves catch with all the little grooves on whatever they're touching, and that causes them to snag, and that causes them to slow down the motion. So friction, force that opposes motion. There are different types of friction, okay? The first type of friction is sliding friction. This is when two objects are grinding over each other. If you ever had to slide in baseball or softball, you understand how much that hurts up, tears up your legs, because you're literally sliding and all those little teeth between your leg and between the ground are catching, and that's causing lots of friction and causing you to get all kind of cut up and stuff. If you try and push a desk or a chair or a bookshelf or something across the ground and you're pushing it, that's sliding friction. It's important to understand that even if something on ice, even though it's slippery, it still has a little bit of friction. So a puck moving over ice will eventually stop because there is some friction there. One thing that we experience very often is rolling friction. Anytime you're in a car or some kind of vehicle and there's a wheel, you're experiencing rolling friction. Okay, so basically what does that mean? There's friction on the axle, right here, and there's also friction between the tire and the ground. So that's the rolling friction. But the difference is that this is sliding. So those two things are literally going to grind over top of each other. Rolling friction is where, think of, kind of like if you put like Velcro down on something and then you pull it up. That's more of the rolling friction. Only one part of this wheel is going to be touching the ground at a time. Only one part of this axle is really going to be grinding up at a time. So what we see here is that as this wheel comes down, it experiences friction when it hits the ground, and then it doesn't really experience friction. So that's a little bit different. It's not pushing, it's not grinding. So they will catch a little bit, but not as much as in the sliding friction. Another one that we don't think about is fluid friction. But you definitely experience this. If you've swam, you know what fluid friction is. That force, you move slower in the water. You can actually see, you can make waves with your force and things like that. So you move your arms around, you can see that force being pushed through the water. Now, it's important to understand that fluid is true for a liquid or a gas. So air resistance actually falls under, air or wind resistance rather, actually falls under fluid friction. So water and air work very similar. However, we can use some properties of fluids to help reduce friction. If you don't know this, you're supposed to keep oil in your car. And that's why you have to get it changed every once in a while, because what the oil does is there's lots of parts that grind together in your car, and that friction is bad. So you want to reduce the amount of friction. So you apply some oil to that surface, and what happens is that oil, we can go back real quick. What happens is, imagine this is your edge of whatever your surface is. The oil is going to fit into all those little grooves, and it's going to create, kind of separation between the two surfaces from really touching together. It kind of fills that space, and they can't kind of lock together as well, and that reduces the amount of friction. Okay, so using oil in your car reduces the amount of friction, and therefore, because it gets in all those little gaps. All right, so how do you make a free body diagram? This is what I want to see, okay? This is as simple as it needs to be, as complicated as it needs to be. But they're used to show the relative magnitude. Remember, that's just an amount or a size, and direction of all the forces acting upon the object. Notice I have gravity. Gravity is always pointing which way? Down, because that's where gravity pulls, okay? I don't want to see the force of gravity going to the right or to the left or up. It should only go down. It's also the size of the arrow that matters. Now you notice this, the normal force and the force of gravity are of very similar size. Therefore, those forces are balancing each other out. This is actually true of these two. These look about the same size. This is the force of friction. This is the applied force, kind of like that example we were looking at earlier. So this is trying to be pushed. If we were to get out a measuring stick or tape or something, we might be able to see a slight difference here. But if this one's a bigger force and the object is moving this way, your force of friction is usually going to be a much smaller arrow. This is not the best example. This should probably be right about here, because that would show that this book is being, or this object or whatever, is being pushed in that direction. Right now from this diagram, I can see all the arrows are about equal size, which means all the forces are balanced. So this object's actually not going to be accelerating. Remember, it doesn't mean it's not moving. It just means it's not accelerating. That's another hard thing to think about. So again, this diagram shows 4 forces acting upon the object. There aren't always 4 forces. There could be 2, 1 or 2 or 3, but this is, kind of an example of what we can see. So now we're going to go over some examples of how to make free body diagrams. So let's say a book is at rest on the tabletop, and we're going to diagram that. So what we're going to do, can't do it on here. So let me pull up the other PowerPoint again. I'm sorry, just keep switching back and forth, guys, but PowerPoint has some things that slides don't have. The slides are just, like I said, edited a little bit better. All right, let's try this again. Okay, so now I can actually draw on this a little bit. So what we're going to do is we're going to diagram this book resting on the table. So the first thing, remember, the first thing you always draw is just a simple square. Okay. So again, don't make fun of my square. My mouse penmanship is not the greatest. So there's my square. If I know the mass, I can put the mass in there. If not, I can leave it just as is. Now the book is sitting on the tabletop. So if it's sitting on the tabletop, it's being pulled down by something, and it's always the same thing. So we're going to draw a downward arrow, and we're going to label that what force? What force pulls things down? Well, it's the force of gravity. So I'm just putting G-R-A-V. You can write it out if you want. You don't have to write it out. You can abbreviate it, but you need to see the F of at least G, force of gravity. Okay. Now, why is that book not falling through the table? Okay. Well, because the table is actually pushing up in the opposite direction. All right, with the normal force, F of norm. Okay, so that's the normal force. So for a book resting on the table, it's not being pushed, it's not being pulled, so I don't see any other forces. I got my force of gravity, that's check. I got my normal force, that's check. If you notice, I tried to make these arrows about the same size because it didn't say it was moving. So these two are balanced. So it's not moving, it's not accelerating. Excuse me, I should say it's not accelerating. Okay, and that is the correct example for all the forces acting upon that. And that's what we can see with their example as well. All right, let's try problem number 2. An egg is free falling from a nest in a tree. This tells us to neglect, which means ignore. So we're going to ignore air resistance. So it just wants us to focus on the falling egg. So again, I could draw an egg, but I'm just going to draw a square because that's what it asks for. Every time you just draw a square. There's my egg. Look at that pretty egg. Now, what if it's falling, what is acting upon it? Well, there's a large downward force. What pulls things down? It's the force of gravity. So force of grav. Now, because it told us to forget about air resistance, we don't need to add it in. But if we did, it would just be a little arrow in the other direction. And why would it be a small arrow? Well, because what is the egg doing? It's falling, which means that the downward force is much bigger. Okay. But for this example, this is what they want us to see. They want us to see the square with the one downward force because they told us to forget about air resistance. And that's what we can see. Here's your egg falling from a tree. All right, let's take a look at problem number 3. A flying squirrel is gliding from a tree to the ground at a constant velocity, which means because it's gliding, there's no wing flaps. Guys, a wing flap would be an applied force. The reason that they're telling us there's not an applied force is to show us that it's moving to the ground. So they're just the natural forces acting upon it. So how do we make this? Well, again, just draw our square. And then what's causing us to go to the ground? Well, we know, nice sized arrow, and that's the force of gravity, right? Now, why doesn't that squirrel just crash into the ground? Well, because it's got its, It's got some skin that it kind of pushes out to increase the surface area, because what it's using is it's using the force of air resistance, okay? So the force looks like fair, force of air, okay? That is the force of air resistance. So the reason the squirrel doesn't crash into the ground is because of that air resistance. It's slowing its fall. And we can see we got the same thing. So gravity pulls on the squirrel down, while the air resistance keeps the squirrel in the air for a little bit. All right, we're gonna do at least one more here. All right, problem number 4. A rightward force is applied to a book in order to move it across a desk. Consider friction. Neglect air resistance. Guys, technically, even if you're pushing something across a desk, because it's moving through the air, it would have a little bit of air resistance, but this is telling us it's going to be so small, we're just going to ignore it. Just don't even worry about the air resistance, okay? And what we're going to do now is we're going to construct a free body diagram to diagram this. So I'm going to give you guys just a moment. I want you to try this one on your own. It's being pushed to the right, so draw your box and label the forces. And I'm going to pause for a minute while you do that, but I'm going to make my box. So I've got my box there. All right, so go ahead and label all the forces that you think are acting upon this object. Okay, let's take a look at how you guys did. So, why is the book staying on the table? Well, it's being pulled downward with the force. It always pulls things downward. Gravity. It's the force of grav. Next, why doesn't it fall through the table? Well, because the table or the desk or whatever we're dealing with is pushing upward on it. With what force? It's the normal. So normal force is keeping it up. Now, this says that it's being a rightward force, so a force going to the right. I'm going to make this nice and large because why? It's being moved, right? It's being moved. So that's why I'm making this a bigger arrow. It's not moving up or down, which is why those two arrows are equal size, but it's being pushed to the right, hence the bigger arrow. So this is the applied force. So force of app. All right, that's the applied force. Now, you may have gotten here and you may have forgotten about one last little force. Maybe you got gravity, maybe you got the normal force, maybe you got the applied force. But remember, there is a force that opposes motion, and that is the force of friction. So there should be a smaller arrow. And why is it smaller? Well, because it's moving in this direction. And this is the force of friction. All right, force of friction. Force of friction. All right, and here we see, and it says, note the larger applied force arrow because size matters. It shows it represents a bigger force. It shows that this is unbalanced. And what does this mean? This means the book is going to accelerate in the direction of the applied force. Okay. Now, skip over some stuff real quick. All right. So we're going to talk about objects' net force, okay? And net force is either going to come out to be balanced or it's going to come out to be not balanced. So let's take a look at what happens when unbalanced forces do not become completely balanced or canceled out by other individual forces. So let's say we're pushing an object to the right with 5 newtons of force, and then someone else is pushing with 5 newtons of force in the same direction. Notice these two, oh, you guys can't see that. Let me get my little laser pointer. So I'm working here on the problem, 5 to the right, 5 to the right. Because these are in the same direction, they're going to be combined. So what's the overall net force in this top object? Well, it's 10 newtons to the right. These are in the same direction, you add them. Now look, I've got 5 newtons of force to the right, 5 newtons of force to the left. They've decided to make this one negative just to get you to think about these are in opposites, but we know if it's in opposites, we subtract. These two are going to cancel each other out, and boom, we have a net force of 0. This is a balanced force. When all the forces cancel each other out and you're left with 0, that means it's balanced. It means it's not going to accelerate. This one, the top one, the 10, that will accelerate to the right. This one, because they cancel out, will not accelerate. Again, we have 2, 5 to the right, 10 to the right, so we have a total net force of 15 to the right. But what happens when those are in opposites? Well, we had 5 to the right, we have 10 to the left. So what does that mean? Well, it's 5 newtons of force, because 5 minus 10 is 5, right? But it's to the left. Yes, it's technically -5, but the negative is just really talking about the direction. So it's actually the bigger one was in that direction, so therefore it's in that direction. Same thing is showing here, the bigger the force in that direction. So there, here we had 5 minus 15, and we end up with 10 from the left. It's important to understand this can also happen with things like this. We've got 10 newtons force upward, 5 newtons of force downward. So what our net force, overall force, is 5 newtons up. So this object is taking off. It's important to understand that unbalanced forces exist when the vertical and horizontal forces do not cancel each other out. So anytime you have a leftover, so like this one's unbalanced, this one's unbalanced, this one's unbalanced, this one's unbalanced. So all of them but this one. This is the only one that's balanced. It's the only one that cancels out. So for example, we've got an object with 12,000 newtons of force upward. We have 800s of newtons force downward, that's gravity. So what is this object doing? Is this balanced or not? Well, we can see 1200 minus 800, they're not, they're in opposite direction. We're going to subtract them. So we end up with 400 newtons in the upward direction. So this is going to accelerate upward. Here's another example. We have the normal force pushing up on the object, gravity pulling down. Those will cancel each other. So you see up and down, 50 minus 50, that's going to cancel. And then we have 20, the force of friction, okay? Nothing over here. So this is actually another unbalanced one. I don't know why they made that friction. That doesn't make a lot of sense. But in this case, it is a net force of 20 newtons to the left because these will cancel. There's nothing to cancel this 20 out. So I think that's what they're trying to show us. We already took a look at this. I don't know why they're showing this again. I don't think we need to go over this stuff. Oh. This one, even though I already accidentally showed you the answer, let's take a look at this. Which of these objects are moving? Well, if I look at this object, that should really say accelerating. That's bad. Which of these objects are accelerating? Because this could be moving, we just don't know. Anyway, 5 newtons of force to the left, 5 newtons of force to the right. Those cancel out. 3 up, 3 down. Those cancel. This is balanced. It's not accelerating. If we take a look at this one, we've got 3 up and 3 down. That cancels, but we've got 5 to the left, nothing over here. So this is unbalanced. This will accelerate. Situation C, we've got 20 up, 20 down, balanced, not going to accelerate. Here we've got 40 up, 25 down. This will accelerate in the upward direction. Bigger force. And guys, that's it for Newton's laws. All right, so I'm going to pull up the classroom. Okay. So what you guys need to do now, if you've not already done so, follow this link right here to get to the BrainPop video. It's very simple. It'll pull up like this. When you go to hit play, it's going to ask you to log in. That's where you use the username BALTCOPS. That's also in the description there. And then the password is all lowercase, one word, BrainPop. You'll click log in. It'll be fine. Say, hey, thank you, hi there. And you just play the video. It's just over 3 minutes long. I'm not going to play it here. Just go ahead, follow that site, and log in to watch the video. When you're done with the video, you're going to answer the questions. on the little worksheet right there, right here. It's like a little quiz. They do not go in order, so make sure you watch the video once or twice, then go ahead and try to answer these questions. Then you do have the practice. Okay, we have the force worksheet right here. So this is going to talk about, what is balanced, what is unbalanced, diagramming some free body diagrams, things like that. Very simple. Fill this out, get it back to me. If you want to do some of these on paper and text me or email me that picture, that's fine as well. Then the last thing you have for day 7 is the exit ticket. Okay, so make sure you guys are filling these out. I have been grading them and turning them back into you, so you should be able to see these grades. Guys, your exit tickets are the main grades that are going in the grade book, so make sure you're doing well on these. This is a summary of the lesson. Take your time. If you need to go back and attempt some ones from before, please make sure you do that. Or if you want to redo them, please make sure you do that. And then just send me an email or something if you do redo them, so I know to go back and change your grade. All right. Again, tomorrow is the first test. So it's very important that you are studying everything up until now. So what is that? Hey, the metric system. Remember, moving the decimal one way or another. Distance versus displacement. Distance doesn't care about direction. Displacement does. Speed, distance over time, and the motion graphs. Okay. Velocity, displacement over time. Know how to do acceleration and what is acceleration. So final velocity minus starting velocity over change in time, as well as speeding up, slowing down, change in direction. Remember, constant speed equals no acceleration. That's really important. You will need to know the acceleration on graphs as well, and then Newton's laws. Okay, so again, you guys will have to take this in person in the building. So make sure you are making the appropriate accommodations so you can get in there and get that done. I'm going to be sending that to your coaches today so that they will have access to the test. You just need to do it in their presence. You can use the calculator. You can use the formula card, which is up here. I'll pull it down here. All right, here's the formula card. It's just a little PowerPoint. This is the metric system up at the top. Here's your formulas. Do not worry about this bottom part, P, E, K, E, T, E. That's all what we're doing next week. So it's really just this top half, all the way down to force equals mass times acceleration. So if you recognize it, you should be able to use it. If not, don't worry about this bottom stuff. We're going to get to that later. Okay. If you guys have any questions or comments, please reach out and let me know. Otherwise, I will not be Zooming with you tomorrow because it's test day, but I'll be Zooming back with you on Monday. Make sure you study, reach out if you need anything. Good luck on the test, guys.